In this video, we are going to be going over the concepts of Lab 5, which is titled Lewis Structures, VSEPR, and Attractive Forces. When it comes to the background, the first thing that we're going to be discussing is the idea of Lewis structures. We know that atoms are composed of neutrons, protons, and electrons. And Lewis structures, which were designed by Gilbert and Lewis, actually illustrate in an atom, specifically, the valence electrons. And if you remember, the valence electrons are going to be the electrons in the outermost shell. Now, in this course, we are going to be focusing on representative elements. And when it comes to representative elements, those are going to be elements in groups 1A through 8A. And remember that the number before the letter A indicates the valence electrons in an atom. Now, we understand that these valence electrons are either going to be given away by metals and accepted by nonmetals, or shared in the case of covalent compounds. But when it comes to Lewis structures and building them, we specifically are going to be focusing on covalent compounds. In other words, molecular compounds. Those are going to be molecules that are built from two or more nonmetals, and they're going to share electrons. Now, understand that a Lewis structure for a molecular compound is actually a two-dimensional representation in which, as I mentioned a few moments ago, the electrons are going to be shared. Now, whenever we have shared electrons, are illustrated using a line. Whenever you have pairs of electrons, that is not shared is called a lone pair. Okay, so understand that specifically in this lab assignment, we are going to be focusing on Lewis structures for molecular compounds or polyatomic ions. Let's now go over the rules of how to build a Lewis structure. The first thing that we need to take into consideration, I'm going to use my highlighter tool, is that you need to add up the valence electrons that are available for bonding. And remember that when we are doing this exercise, we need to take into account specifically what is the subscript that it is available in the chemical formula. So to give you guys an example, let's say that we have the covalent compound CO2. If I'm trying to count the valence electrons available in this molecule, I know that carbon lives in 4A. So it's going to contribute 4 valence electrons, but because there's 1 in the chemical formula, I'm going to multiply that times 1. Oxygen, on the other hand, lives in 6A. So that means that each oxygen is going to contribute 6 valence electrons, but in this chemical formula, I have 2 of them. So after I show the result, 4 times 1 is 4, 6 times 2 is 12, that I add. So what that means is that in this chemical formula, there are 16 valence electrons available for bonding. Then after that, you can actually build a trial structure. This is what I call the skeletal structure. Remember, technically, when we are trying to build these, you could do it through selecting the element that is the most metallic, or the one that has the highest metallic character. Another one trend that you can utilize once we go over it in class is electronegativity. It tends to be that the least electronegative atom is in the center of the compound. Now, understand that skeletal structure, for every line you draw coming out of that central atom, you need to subtract 2 electrons, because every line represents 2 electrons. And understand that you're going to then distribute the remaining electrons respecting the octet rule. And we always start from the outside atoms, okay, first. And if there's any leftover electrons, then we put it in the central atom. Now, it is important to note that there's certain trends that need to be remembered. Hydrogen only needs 2 electrons to have a noble gas configuration. So that's why the normal bonding pattern for hydrogen is the letter H with a line. Other than that, you don't need to put any dots on hydrogen. Okay? As you can see on page 2, there's actually figure 2. It goes over a flow chart of the work. But let's continue. One of the things that I should mention before I move forward is actually the idea of what happens if my central atom doesn't have enough electrons and it needs an octet. So what we do in that case is that a pair of electrons, how many are needed, are going to be taken from the outside atoms, and they're going to be shared into the central atom. And that's how we create double bonds and triple bonds. On page 3 of the lab, then we start discussing about VSEPR rules. Okay? VSEPR is specifically, let me highlight it, the valence shell electron pair repulsion theory. So what this means is that, as we know in everyday life, and if you don't know, that's okay, that like charges repel each other. So how we apply that to molecular compounds is that if you have atoms that have electrons, okay, what they're going to do is that those electrons, because they have negative like charges, are going to repel each other, and they're going to adopt geometric forms just because they need to be separated from each other because of the charge repulsion. Now, that actually results in these covalent compounds generating certain structures. Now, as you can see in table 1, which is actually taken from the textbook, you can see the different molecular shapes that are adopted by molecular compounds. Now, one of the things is that in order to utilize VSEPR theory, you really need to practice Lewis structure. That's why we are doing it in the lab. So understand that when you are going over VSEPR rules, it is important that you know what is an electron group. In electron groups, They come in 4 flavors. Understand that the following terms that I'm talking about represent one electron group. The first type of electron group is going to be a lone pair. So that represents one electron group. A single bond represents one electron group. A double bond represents one electron group. And lastly, a triple bond represents one electron group. So if I continue utilizing the same example, I'm just going to illustrate on the right side of the notes the Lewis structure for carbon dioxide. So in the Lewis structure for carbon dioxide, carbon is the central atom, and on either side you have oxygens, each oxygen has 2 lone pairs. Now, for those students that need a little bit more help and would like to see how I actually came up with that structure, I'm going to explain it right now. So, remember that we calculated previously that there's 16 electrons available for bonding in this structure. So that means that after I've counted my valence electrons, I know that those are the only electrons that need to be placed in the structure. When I look at electronegativity trends or I look at metallic character trends, I know that carbon is more metallic compared to oxygen in general. So I know that carbon is going to be my central atom. Now the other elements that we have here are oxygen. Then I understand that this already took care of 4 electrons. 2 electrons here and 2 electrons here. Taking that into consideration, I'm going to subtract 4 electrons from here, and I have 12 electrons left. So at this time, then I'm going to place the remaining electrons on the outside atoms first, because oxygen, each of them is sharing 2 electrons with the carbon, then each of them is going to get 6 dots. Placing these 6 dots onto specifically the carbon atom, onto the oxygen atom, then that means that I already used the remaining 12 electrons, so that means that I don't have any electrons left. Now, at this time, my carbon atom does not have an octet, so at this point, I can select a pair of electrons from this oxygen and share it in. So that means that this carbon is going to have a double bond with the oxygen on the right and at this time my carbon atom still is missing electrons in order to have its octet. It only has 6. So I can select a pair of electrons from the oxygen on specifically the left side. And when I share those in, then my final molecule is going to be a carbon atom that has this arrangement of electrons. Now, if I count those 16 electrons, because I want to illustrate it for those students that are still practicing, we have 2, 4, 6, 8, 10, 12, 14, 16. Those are my 16 electrons in the system. Now, going back to the task in hand, I know, and I'm just going to box it here in pink, that this is the structure for my CO2 molecule. So when I'm doing VSEPR rules, what I need to take into account is how many electron groups are going to be around the central atom. For this molecule, my central atom is carbon. So carbon in this molecule is going to have 2 electron groups. And what are the 2 electron groups? 2 double bonds. Okay? Because remember, each double bond represents 1 electron group. So that means that for CO2, as you can see in our table, it has 2 electron groups, and a molecule that has 2 electron groups is considered linear. And most of the molecules that we explore in this course are going to have 2 bonded atoms, no lone pairs, and the angle that separates these oxygen atoms to the central atom, so the angle here, that is 180 degrees. Okay, that's why we have this here. Now, understand that we also have the molecular shape, and molecular shape is affected by lone pairs, but because we don't have any lone pairs attached to the central atom, in this molecule, we know that linear is the word that we utilize in order to specifically determine how many bonded atoms we have in the system. Okay, and as you can see, that's how we determine the electron group geometry, bond angle, molecular shape for this particular molecule. It is important that you have the correct Lewis structure in order to designate the electron groups, and then after that you will be determining the electron group geometry, the bonded atoms, in order to determine the bond angle and the molecular shape for different molecules. So make sure that you practice the Lewis structures that are in the lab specifically.